Hi, my name is Maggie Monahan, and this is my Lab 5, Faraday's Law. The purpose of this lab is to model the magnet and tube interaction computationally, and also to compare this computational model to the observed data. Some physics principles that are used are Faraday's Law, which states that the EMF is equal to the negative change in flux, the Biot-Savart law, and Newton's second and third law. Also, we will observe that moving objects can induce currents. In this lab, the bar magnet induced a current in each of the rings of the aluminum tube. In this lab, first, the magnetometer app was used on a phone in order to determine the north side of the bar magnet. Then, the aluminum foil tube was held vertically and the magnet was dropped through the tube 5 times, and the average time was recorded. This process was recorded using a camera, being able to see the magnet both enter and exit the tube in order to be able to get an accurate time. As the magnet fell through the tube, it was tilted to the left and the right towards the edges of the tube. If the magnet was falling in free space, this would not happen, and it would also fall faster. In this lab, we can't use a ferrous metal because the magnet would not fall through the tube. Rather, it would get stuck to the sides of the tube. The length of the aluminum tube was 0.32 meters. The width of the tube was 0.013 meters. The inner radius was 0.025 meters, and the dipole moment, which was found during an earlier lab, was found to be 2.44. After the measurements were recorded 5 times, the average time was found to be about 1.21 seconds. Next, this lab was modeled computationally using GlowScript. In order to do this, first, the geometry of the tube and the scenario was set up by inputting the length of the tube, the width of the foil, and the inner radius. Also, the mass and the dipole moment of the magnet were also inputted. In step 2, a function is created to calculate the magnetic field of the bar magnet. Also, a function is created to calculate the magnetic flux of each ring due to the falling magnet. Next, the gravitational force on the magnet, the current in each ring, the B field at each ring, and the magnetic force on the magnet is calculated. Here we have the output of the code, and it shows that the magnet was in the tube for 0.723 seconds. This, however, is much lower than the value observed in the real-life scenario. So, when the magnetic dipole moment is changed to 3.21, the time the magnet was in the tube was increased to 1.21 seconds, which is what the average was calculated to be using the data. It is also possible that discrepancies between the time observed with the data and the time that was outputted by the code could be due to air resistance in the real world, or also human error in calculating the time it took for the magnet to fall through the tube. There were 2 questions that we were asked to answer upon concluding this lab. First, what if the resistivity of the conductor were reduced as close as possible to 0? How would the dynamics of the falling magnet change? If the resistivity was reduced to 0, the current in the tube would be greater, making the magnetic force much greater than the force of gravity. Because the magnetic force is much greater than the force of gravity, the magnet is unable to fall through the tube. The second question was, what if holes or slots were cut into the tube? How would this affect the ring currents in the model? If holes were cut, there would be different cross sections in each of the rings, which would result in the total current being much less. In conclusion, this lab was a great way to observe Faraday's law in real life, and also to observe how magnets react while falling through conductor. We were also able to observe induced currents due to moving objects, and to compare the computational model to the observed model. In this scenario, I observed that the computational model had a much lower time as compared to the real-life scenario, and this could be as a result of air resistance and also human error in calculating the time. Thank you so much for watching.